Hello, I'm Lucas. I work at VirtusLab. There's a small slide about me. I'm Scala developer advocate, so I'm the person you can come to and complain if you have any issues, problems, or feature requests regarding Scala. We value feedback very much, so I will gladly hear you out. You can also follow me on Twitter, and I will also add more channels like Mastodon soon. Okay, so let's go quickly through the agenda of my talk. I'm going to talk about Pulumi, and Pulumi is a DevOps tool. So I'm going to start with a very short explanation what the situation in the DevOps world is right now, and what can we do about it. Then we will very quickly go through the Pulumi itself, what it is, how it works, and then we are going to go into a small Pulumi program to see how those programs work, how they look like, and then we are going to do the promised thing, so ship a true AI-based product. Okay, so let's start with what DevOps is, or rather, what the situation in this ecosystem is. So doing DevOps is sort of like what you see on the picture. It's like riding on a unicycle and juggling, but everything is on fire, and you are trying to, not fall. So the whole story is that in the beginning, when the DevOps movement started, there were promises made to the developer community, and those promises were that we were going to be empowered, we were going to be able to take responsibility into our own hands, to build stuff without silos, without separate administration teams that do all the operations. We're meant to lift the whole stuff that we build and run it. So we wanted to have this capability, and then, well, it turned out not to really work that way. So current situation is that most companies see DevOps teams that specialize in Kubernetes YAMLs, in HCL for Terraform. They also conjure and adjure stuff in cloud, hopefully doing infrastructure as code, which isn't a given. We are back to situations where all the infrastructure stuff requires conversations and tickets with operations teams. And what is the worst thing for the business is if we, developers, do something stupid and push that to production on Friday in the evening, obviously, somebody else gets woken up in the night when things go down. So can we do better? Yes, we actually can. The solution is the newest kid in the block in the infrastructure space, Pulumi. Pulumi is, in the words of Joe Duffy, the CEO of the company, is a tool that allows you to use your favorite language to declare and work with any infrastructure that you would like to work with. So how does it work? What does it mean that you have your favorite language available? Pulumi maintains an ecosystem of multiple languages that are supported as official SDKs. They have support for TypeScript. They have support for JavaScript, obviously, because the same thing. They have Python. They have Java. They have Go. And they have .NET. So everything that works on .NET also is available, F#, for instance. So VirtusLab started cooperation with Pulumi some time ago. We helped to bootstrap the initial implementation of the Java SDK. Pulumi gracefully taken this SDK onto its own wings, and we have started working on another set of SDKs for languages that we care about. So we have built SDKs for Scala and for Kotlin. Let's talk very quickly, because 4 minutes. Okay, that's not that bad. Let's go through an anatomy of an example Pulumi program and what are the most basic blocks that you use to build such a program. So to keep in the tradition of the famous meme, we are going to first draw some circles, and those circles are, there are stacks in Pulumi. So a Pulumi program, when you write it, is just a blueprint, just like a class in object-oriented programming. When you instantiate it, so when you run a Pulumi program, it actually creates a stack. A stack is an instance of your blueprint. It's a concrete representation of what has been deployed, what has been created in the infrastructure layer. There's also a state that Pulumi holds wherever you want Pulumi to hold this state. So there's a state associated with the stack. And the program is composed out of three things: resources, inputs, and outputs. So resources are things that we want to declare, that we want to have created. And resources are best understood as infrastructural CRUDs. So they have the same set of operations like basic CRUDs. They can be created, they can be queried, they can be updated, and they can be deleted. In this case, we only create an S3 bucket for pictures of cats, obviously. And what is important here is that all the resource constructors take values that are inputs. So inputs are the information necessary to create any given resource. What is actually returned is a resource wrapped in an output. Output is a dynamic value. It's something that will be created in runtime. There are actually two types of outputs, but that's smaller subject, things that are resolved immediately and things that are coming from the engine. So things that only are resolved when engine resolves those values in the cloud. Finally, outputs can be used in the final bit of a Pulumi program. In this case, we have a stack exports clause that is from Besom, which is the Scala SDK for Pulumi, where we say that our stack should export one property, cats URL, that points to the website endpoint output on the cats bucket. Okay, so here's a bigger chunk of a program, how it works. This is using AWS API, and it's basically doing the same thing. It's just declaring two buckets this time, and the stack export just exports those two values. It's important to notice that exports allow programmers to do very interesting things, because Pulumi is composable. So stack exports are things that are kind of like set out properties on an object. You can read them further. You can read them in the future when the stack is deployed. So this composability has multiple levels. Stacks can depend on other stacks via stack references, so you can just call another stack in your program and pull some exports out of that stack. Best way to imagine that is, in one stack we deploy a Kubernetes cluster, and then to be able to work with this cluster, we export kubeconfig, and then in the stack that deploys infrastructure onto the Kubernetes cluster, you just reference this kubeconfig to feed it to the provider that will then do all the work with Kubernetes for you. Moreover, there are built-in components that allow you to aggregate in a logical way resources that you want to treat as coherent whole. So something that has all the necessary bits that have to do one function. This can also be extended further. So custom components can be then turned into Pulumi packages. And that is really interesting because it means that if you define such a coherent whole, you can then export it for other users in other languages to use. Okay. There's some stuff that is differentiating Pulumi from different tools in this area. And I think the most interesting ones are those two. Automation API is something that allows programmers to use Pulumi in a programmatic way. So you basically embed a Pulumi program inside of your program. And with Besom, it's possible to do this, or rather will be when this pull request is merged. You can embed a Pulumi program, and it can run with a Zio stack, it can run with Cat's Effect stack, it can run with whatever uses features. So you can then control infrastructure from, let's say, Kubernetes operator, or if you have a multi-tenant infrastructure, you can create a controller that will run in a separate space in the cloud, and it will be tasked with creating environments for your tenants. Okay, and the last thing is Pulumi CrossGuard, which is a feature that is very interesting from enterprise perspective because it allows to apply basically a predicate. So you write code, you can just write a function that checks something on all the resources it can touch. So then you can imagine that as an iterator, that goes over all the resources that Pulumi manages in your infrastructure and applies a predicate or applies a change to those resources. Very good for management of huge piles of infrastructure. Okay, so that's the time. We have to start, and I'm going to sweat a bit. So we have to draw the rest of the fluffy hole. And I have some idea, because this is, I think, 5th or 6th time I'm giving this talk, but I have changed it. I have changed it a bit every single time I have given it, and I always had at least 45 minutes to do this, but we have 20. Okay, so this is what we are going to actually build. We are going to deploy a K3s cluster. I'm a cheapskate. I don't want to pay to Amazon because it's kinda expensive. So what I want to do is I want to use something that is nice and cheap. And that is, in this case, Hetzner. Hetzner is a provider of cloud services in Germany. It's not a very big provider. It doesn't have all the shiny bits like S3 compatible storages, but it has very nice, very speedy, and very cheap VMs. And that's good for me. So we are going to deploy a K3s cluster with 3 nodes. A K3s is a distribution of Kubernetes. Let me quickly come here. K3s is a simplified version of Kubernetes that has a lot less moving parts. Basically, you can install it in a very, very, very easy way. Of course, we are doing this in a scenario where we are a startup. We are going to move fast and break things and don't worry about things not working. So obviously, we are going to install K3s by just running a random script from the internet, because why not? What could possibly go wrong? I mean, we are going to use Scala because it's a high-performance typed functional language, and we value those things very much. We are also going to use something very nice and shiny indeed, which is PostgreSML. It's a way to run AI models in Postgres, because it seems to be a good match to make, and it works, so that's good. That's good for us. VCs are waiting for things to happen, and we are going to use whatever is usable at the time. So going back to architecture just for a moment. So we are going to then deploy our stuff into K3s, which is going to handle the scalability that we have promised scalability to our VC. So yeah, we have to have Kubernetes. And we are going to deploy our service in a deployment with the PostgreSML running all the AI ops for us, because that's simple. Okay, that's a bit too far. So I have taken the liberty to actually deploy the whole thing when I was waiting for my talk to start. I did that because, you know, if there were any network issues, this deployment that takes just 12 minutes, because PostgreSML downloads basically half of the Hugging Face with the models that it has inside. Takes at least 500 seconds, I think, to deploy. So I've taken the liberty to actually do this, and we have this whole thing deployed. So we are going to actually go through the code base, but the whole thing works. You can see this here. The code itself, I don't think this works correctly. No. Oh my. Yes, demo effect. Maybe? No. Well, it's borked. Okay, let's go through the code. Is this big enough, or is this too big? I think it's a bit too big. What was it? I think it was, yeah, better? Cool. Okay, so we have our infrastructure and we have our application. Our application is a very simple thing. It doesn't use any very fancy tech. It's just using Tapir and deploy some endpoints. There's the most basic HTTP server possible, but we are using Loom because we are scalable. Remember, we are a startup. And we, oh, sorry, I forgot I have to check out the other branch. Cool. And we have the PostgreSQL with ML taste of doing machine learning by just running queries. So we have the embedding thing, we are doing the retrieval augmented generation thing, which is basically taking documentation of Besom project, then running that into the table that will hold information about posts and parts of documentation with the embedded form of that article. That allows us to do very nice, very simple vector comparison that allows us to find content that is similar in a semantic way to what we want to ask about. So we are using Magnum, we are using HTMX because obviously we have to be on the hype. And we are using HTTP version of the OpenAI client, which provides us with very nice API to run queries against OpenAI. The slow part in this application is actually not the local PostgreSML database. It's actually OpenAI for some reason. I think they are overloaded lately. Okay, but that's the application. Let's quickly go through our infrastructure then. So as I mentioned, we are deploying a K3s cluster, and K3s cluster will have to have some locations where it has to have some machines to run. So first thing is we create a vector of locations. Those locations are actually codes of locations for Hetzner data centers. I think it's Weisenberg, Nuremberg, and Helsinki in Finland. We are going to work with pure VMs, so we have to provide an SSH key, and this is a resource for Hetzner Cloud. We just create a key with the public version of this, and we also load the private key that we are going to use to authorize with the machine. So the public key goes onto the VMs, private key we are going to use to run commands on those VMs. We then create a server pool. Again, very straightforward. We just create a range, 1 to 3, because we want 3 machines. We create an instance of server. We provide a type of the server. This one, I think, has 4 CPUs and 4 gigs of memory. Enough for our startup at this time. And, you know, we're not going to go into our budget. We can go into vacation. Okay, so this is going to run with Ubuntu. We are going to use Modulo to spread the servers on the locations, provide the SSH key, and cool. That part is basically this bit. So that's the creation of the whole stack of machines on Hetzner. Now, the next bit is we need to install K3s onto those machines, and we also have to provide information about our container registry, because that's what runs on Kubernetes. We want to have ability to use GitHub's container registry because it's free, and therefore we have to build some YAML because that's how K3s is configured, obviously, and be able to then put those YAML files onto the actual machines. So how do we do this? We need the token. Just to quickly elaborate on this, Pulumi has a very nifty feature that allows us to store all the secrets, all the configuration information per stack, so on a stack level, so per instance of our infrastructure, encrypted in our Git repo. This requires that you provide a password, but as you can see, we have secrets, so all the tokens for all the services that we are going to use. We have Cloudflare, we have GitHub Docker token, we have OpenAI token, and that's the last bit is just configuration. So what we have to do, we have to create all those instances of K3s. K3s is a leader-follower setup, so we have to install the leader node and then fetch the token that allows other nodes to join. So that's exactly what we do. We split our pool of servers into a leader section, a follower section, then we create a connection to the leader, and then we, well, install by running just the shell script from the internet. But, you know, we read about security, so we are using WireGuard as VPN because nobody can then listen what we're doing in our cluster. So there is some security, not in the best places, but there is. We can also see that commands are here treated just as other resources, so they are CRUDs. We have create command and we have delete command, and that allows us to do very nice things. We can specify operation that will happen when this command is doing the creation step, and then we can provide the delete step that will clean up when the resource is being deleted. We then use another command, which is basically just wrapped cat. So cat command, obviously, that has that is reading the file in the guts of the file system where K3s holds the token itself. So this command will pull the token for us, and then we'll run this command. So this is the insert GitHub container registry token command, which is basically this bit. It's just make dir and a cat that puts this bit of YAML inside of this file in the registry's YAML file. Cool. Okay. Then we have to do some hand-wavy restarting of the K3s leader to pull the token and use the token for container resolution. Then we have to pull the kubeconfig from the leader node. That leader is actually hosting the kube API instance, so we need this file to be able to operate on our cluster. And then we go to the followers. So as you remember, we have split our set of machines into single leader instance and two followers. So we have a sequence of followers. We then create the connection. So basically the same thing. We start K3s on followers. This time we provide the K3s token, obviously by running shell scripts from internet. And then we do the same thing, because other nodes also have to be capable of pulling containers from GitHub Container Registry. So we also insert the GHCR token. We also have to restart those followers, and then we finish with this thing. So Besom is actually purely functional. That means that stuff that you don't use doesn't work. Stuff that isn't referenced doesn't work. It doesn't happen. It doesn't have any side effects. So in this way, all the outputs that we use have to be somehow referenced. That is going to be very clear at the end, but for now, let's just remember that everything that we do has to be chained into evaluation, just like you would have with Zio or Katz effect. Okay, so then we create a small bit that just fetches all the IP addresses as properties from the servers. We do some small adjustment to the kubeconfig because the default file that is created by K3s has name of the cluster set to default, and it's set up to access the local node, so it has a loopback address. We replace that with actual leader IP property that we have read from the server, and then we create our K3s object that represents the whole bit for us. Okay, so finally, we go to deploying infrastructure onto the Kubernetes. And if you are familiar with YAML-ish version of Kubernetes manifests, this is basically the same, but with types. So here, first thing that we have to do is we create a provider with the kubeconfig that we have pulled from K3s that we have deployed. And we then create a small effect that will just write this kubeconfig to a file in the current directory where we are running, so that we can use this very nifty, oh, no, you haven't seen that. What was it? Set x. That's bad. Okay, it's expiring tomorrow, so not that bad, but yeah. Oh, yeah, there's this trick. So you can append a kubeconfig, local kubeconfig file to your global kubeconfig variable, and that allows you to do this. So we can then kube context, and we have this deployment here. Voila. So let's check whether we have all those things that I mentioned that we have. Yeah, they are here. Okay, deployment to Kubernetes. This part like I mentioned, is just YAML rewritten to Scala, but it's Scala, so it's typed. We create a namespace. Obviously, we have to pass the provider everywhere because we want to create those things in this particular cluster, not any other one. And there's a reason why also I have disabled this bit. So this prevents Pulumi from using the default Kubernetes provider anytime. We don't want to do that. We always want to specify the cluster on which we want to deploy anything. And trust me, you want to do this. So we specify some values that will serve as, that will serve as ports that we'll use. And then we deploy the database. So PostgreSML instance in a stateful set, just as we should. We pass the labels here. We provide the image here. That's not the very nice way, but that's how they want this container to be executed. Sorry, with a tail f def null, because it closes if you don't do this. We have some readiness probes. We have liveness probes because we are good citizens in the Kubernetes cluster. And then we expose the ports. Everything as you would have it in YAML, but typed. So we then build a service, which is only going to be used with this single instance of Postgres, but we need that to have a stable identifier in the DNS inside of the cluster. And then we swiftly move to actual deployment of our application. How much time do we have? 4 minutes, good. Plenty of time. So first thing that we do, we get the host from the service because we want to use it as part of the JDBC URL. Then we create the deployment. So deployment, we have one replica. We will worry about scaling later on. But we pass labels for application. So those labels are just the classic app with a name of the application bit. Then we have container args, which allows us to describe all the stuff that we have in our application here. So all the things that our container needs. And you can see that we are passing OpenAI token as the environment variable here. Here we have version 03 of our application running here. Readiness probe, liveness probe, all the usual stuff. And then we have the service and ingress. So draw the rest of the fluffy all. Here we have all the stuff. In the end, the last bit that we do is that we configure Cloudflare. Cloudflare uses the token from configuration again, and then we create DNS A records so that we can access our application from the internet. This is my private domain, and I'm using it to host this. We also pull the Cloudflare zone ID to be able to know which zone we want to change in the Cloudflare provider. And that's it, basically. At the end, that's functional programming. We have to return something, so we return a stack. We pass all the things that are dependencies, things that have to be evaluated for the stack to be complete as arguments to the stack itself, and the things that we want to export, things that we want other users of Pulumi programs to be able to fetch when they use stack reference to our stack. We pass those things as exports. So in this case, Pulumi deploys that and outputs the kubeconfig path and the nodes, the set of IPs of the nodes that we have created. So application itself should be somewhere here. Oh, it's gone. Maybe it's not that gone. No, we don't want that. We want this. OK, so that's the deployed application. I hope it works. So like I mentioned, it took all the stuff that is in our documentation for Besom and fed it to PostgreSML, which did embedding part. And now we are capable of doing RAG-based generation. So we have things that are describing how Besom works. So what is lifting? And now we have to wait for a bit. Sorry for the design. This is obviously designed by a programmer. And yeah, we have something that looks kind of all right. Sorry for justified text, but designed by programmer. And yeah, it kind of works. It also has, from what I recall, it also has an API that, oh my, I went overboard. Let's ask it about what are outputs. Oh my. Oh. Did I break it? Oh, yeah. Yeah, obviously. Yeah, the speedy open API. Okay, so it seems to work pretty fine. Now, there's only one bit left. Sorry, I am out of time. But I will let you go to the dinner. I just want to share one thing. I've shielded on the internet that we have something very interesting, and we have that indeed. So, without further ado, this part where we deploy Scala application, you know, with Postgres, we can't do much, but with Scala applications, we actually could have some more safety, because this is kind of meh. So you have, excuse me, you have to pass configuration via envars. It's just a string here. You have to pass this way. What if you actually forget to deploy something? What if you forget a value? So let's change a value here. Let's add configured container args, and let's hope that it works. Okay, so it stops compiling, actually, and that's good, because the bit that is missing is actual configuration. We don't need this thing, but we need to take a little piece of code from here. So Scala is a wonderful language that can do stuff that other languages can't do, and we are going to leverage that fact. So in this case, metaprogramming APIs are going to allow us to make sure that we have actually provided all the configuration that our application really needs. And the interesting bit is, as you can see, we have only specified a container. So introspection is being done by Besom CFG module that I'm working on, and it's in, well, POC, as you can see here. It allows us to have introspection into applications built in different ways, in this case containers, and pull the properties, the necessary dependencies in terms of configuration, and then validate that the infrastructural program is correct, that it provides all the values that are necessary for our application to start in a sane way. So we can just comment this out and see what really happens. And the best way to see this error is just to run compile from console. Yeah, a lot of stuff. Oh, no. Why? Oh, no, sorry. My bad. We didn't want to compile application. We wanted to compile infrastructure. And here we have the error. So 2 properties are actually missing from the configuration for this container. It wouldn't start correctly. So we have caught a big error that would fail our deployment. We have caught it and compiled them. And that's all. Thank you.